So I'm Dominic. I'm the Engineering Co-Director of the Network Quantum Information Technologies Hub. Our hub is about quantum computing and quantum information processing. So our goal is to advance various quantum computing technologies to the point that industry is really excited about them and will take them on and start building the quantum information processing machines of the future.
Quantum computer is going to be used for certain problems where even the fastest computer in the world may take billions of years to find the answer. So what you see here is actually a very realistic model of the quantum computer prototype we are building at the University of Sussex. So there's maybe two technologies which have been recognized to have specifications sufficient where one could imagine building a quantum computer. One of these technologies is superconducting qubits. The problem with this technology is that you have to cool the actual microchip all the way down to minus 273 degrees Celsius. And doing this is unbelievably challenging. You can do this with 10, 50 or maybe 100 qubits. But how do you go about building a maybe billion qubit quantum computer? And so what we've done here at the University of Sussex, invented technology which operates at room temperature with very mild cooling. And so we can really imagine to build a large-scale billion qubit quantum computer.
So we're using trapped ions to try and build a quantum computer, and each single ion represents one quantum bit of information, so one qubit. And we can scale this up to trying to move from just a few atoms in the lab to methods which will be scalable for thousands or even more ions. At Sussex, we're using specific methods where we use microwaves to replace some of the lasers. So this simplifies some of the engineering challenges we have because we can blast our whole architecture with microwaves rather than aligning individual laser beams.
Applications range from the financial sector into science, into nearly all the industrial sectors. So in the next 2 years we are in the process of completing a prototype for this technology. We're also in the process of forming a commercial entity where we can now build large-scale quantum computers and not just work on the construction of the hardware, but also work with companies to find the most interesting problems to run on the early hardware.
We have spinout technologies. There's one, and that's using cavities. Now a cavity is effectively two mirrors close together, and if you put something inside a cavity that wants to emit light, the cavity kind of amplifies the emission, if you will, it enhances it. Now, in the quantum world, we use the light to do quantum information processing, but in the real world, you could put a virus in that cavity, and you could sense the fact that that virus was there. So you'll see a spin-out company that's using this cavity technology to create a virus sensor.
The application that we're illustrating here is a future application in biomedical diagnostics. So for example, one could use a blood sample introduced into one of our instruments, and the instrument would be able to detect and characterize different virus-type particles or other types of particles, or indeed chemicals, in that blood sample to provide information to a clinician who can then use it for diagnostic purposes. So the flu is a virus, and the virus particles are about 100 nanometers, so about 100 billionths of a meter in diameter, and they're roughly spherical. And what our device can do is it can sense and characterize particles of that size so that you can potentially use it to identify flu viruses in a fluid sample. The current techniques for detecting particles of that size are mostly capable of measuring lots of particles at once. Our particular technology allows you to measure individual particles, but not only measure them, to trap them and study them for prolonged periods of time as well, so that you can identify them and you can understand them better.
These are great stories because it's about lab scientists getting interested in spin-out companies. It's about jobs being created. It's about people making investment, exactly the sort of thing that the program was designed to do. We think there are areas like big data, like search problems, big search problems, like machine learning, where the way a quantum computer works could make them more efficient or faster or cheaper. So big decision making, that sort of thing. But industry are vital to what we do in several ways. In a university environment, we can produce a prototype. But of course, industry knows how to produce them in volume and in numbers. So we need people helping us on that side. We need industry to tell us what their problems are, because of course, we don't know what the business problems are, and some of them we might be able to help with. We have a great team of people in NQIT to help us engage with industry. So all I would say is Google NQIT and you will find us.